A proportion is an equation that states that two fractions are equal. So you can see the example I have here is that I say 2/5 equals 6/15. You can check this based on your knowledge of fractions. If you took 2/5 rather, and you multiplied both the top and the bottom by 3, we would get 6 on the top, we'd get 15 on the bottom. You can see that that's a true statement. And this sort of a technique can work, but that's not what we're going over right now. I'm going to look at a different way of checking to see if two fractions are equal, to check to see if a proportion is true, in other words. And we call this cross multiplication. The book actually calls it a cross product, but yeah, that kind of rubs me the wrong way, because a cross product is something we talk about in other math. So I'm going to call it cross multiplication, because that's how I learned it. So what I mean by cross multiplication is you take the diagonal numbers multiplied by each other. You take 2 times 15, and that should be equal to 5 times 6. So 2 times 15 equals 5 times 6. As far as why this works, as far as why it works, yeah, it kind of uses something we haven't covered yet. I'll just go ahead and say that it does work. So if we wanted to solve something like this, if we have 6 over n equals 15 over 10, basically this is asking us to rewrite this fraction so that we have, figure out what n has to be in order for these two fractions to be equal. It's harder to think about if you think about it in terms of fractions, but if we're thinking about it in terms of proportions, we have two fractions being equal, then we know the product of these, n times 15, or 15n, I'm choosing to write it in this order, must be equal to the product of these, which is 6 times 10. So we get 15n equals 60. And based on what we were just seeing for solving multiplication problems, I know that to find n here, I would take 60 divided by 15, which is 4. So 60n, is 4. So to check this, what I'd do, I'd just plug it back into the original equation. I could say 6 divided by 4, question mark, equals 15 divided by 10. So this is the original equation here. I'm just plugging in a 4 for n. Now, it might be a little weird to, I don't know. I think what I'd probably do here to check to see if these are equal is just reduce both of them. I'm noticing I can divide both top and bottom here by 2, that giving me 3/2. On this side, I can divide top and bottom by 5, giving me, again, 3/2, which you can verify that those two fractions are equal in that way. Alright, so something that we haven't seen much of yet is that usually, if you're just used to arithmetic, you're used to using x as something to mean multiplication. We no longer use x as multiplication when we're getting into the realm of algebra. We're instead going to use dots to represent multiplication. You can see that's what I've been doing right here. I used 6.10 instead of 6x10. It's because we want to be able to use x as a variable. It's the same way I was using n as a variable up here. So, in any case, to solve this proportion, I'd do the same thing as the previous one. I'd go ahead and say that 40 times x equals 28 times 100. That's 40x equals 2800. And that gives me x equals this number, 2800, divided by 40. I could just ask my calculator what that is. I mean, I could go about the process of reducing it, but I'll see if this comes out nicely. And it does. We get 70. Let's look at another way we could check our work here. 28 divided by 40, question mark, equals 70 divided by 100. So I could reduce both my fractions, but there's actually a little bit easier way. I'm going to just try typing both of these fractions into the calculator and seeing if they give me the same decimal. So 28 divided by 40 gives me 0.7. 70 divided by 40, also 70 divided by 100, also gives me 0.7. So you can see both of these evaluate out to 0.7 when I plug them into the calculator. And, well, it's pretty clear to see that these are the same number in that case. Here we have another example. 8y equals 12 times 50. So I get 12 times 50, which is 600. So y must be 600 divided by 8, which gives me 75. Let's check this one. 12 divided by 75 equals 8 divided by 50. 12 divided by 75 is 0.16. 8 divided by 50 is also 0.16. All right, this one right here, we're looking at taking, this is really complicated because we have mixed numbers and we're doing division of mixed numbers, and there's all sorts of stuff going on here. So before I really even get into the cross multiplication of this one, what I'd really like to do is to convert both of these mixed numbers into fractions. And to do that, I'm going to take 2 times 2, which is 4, and add that to the 1, keep the denominator the same. So this fraction, 2.5, becomes 5 halves. Or sorry, this mixed number becomes this fraction. On the bottom part, I would take 3 times 2, which is 6, add that to the 1, and we get 7 halves. And so we get another fraction there. Now, it's still a fraction, and we're still dividing fractions, but that's a lot easier, and especially once we do this cross product here, the cross multiplication rather, we actually kind of get rid of all this division of fractions nonsense. So we get 2 times 5 halves is equal to w times 7 halves. Alright, well, 2 times 5 halves, the 2 and the 2 that's in the numerator right here and the 2 in the denominator right here cancel out. Remember that if you don't write a denominator, you can always pretend that that number was in the numerator, because you could say it's something over 1. That's why I called this 2. I said that it's in the numerator. It's on the top part of a fraction. And that's why it was able to cancel out with the 2 here. So in any case, we get 5 equals 7 halves w. Now what I'd like to do is I'd like to take this 5 divided by 7 halves, because that's what I did on all of these. I said w equals the number that's on the other side of the equation divided by 7 halves. So I've reintroduced this whole dividing by fractions thing. But we've already dealt with fractions. We know that this means this would be 5 times 2 sevenths. I said 5. 5 times 2 sevenths. We multiply by the reciprocal of the number we're dividing by. So this was 5 divided by 7 halves, so it's 5 times 2 sevenths. Now I can multiply these together. Again, this 5 is in the numerator, the top part of the fraction. So I can do 10 on the top and 7 on the bottom. We get w must be 10 sevenths. So to check this, I know I'm kind of way out here. To check this, we could do 10 sevenths divided by 2, question mark equals. It's definitely worth our while to check it when there's all this additional stuff going on. So question mark equals 2.5 divided by 3.5. As far as plugging these into the calculator, I'm actually just going to call that 2.5 and this one 3.5. That would be another way I could have dealt with this one. Instead of working with fractions, I could have just called them 2.5 and 3.5. That'd probably be easier. Whatever, it's done. Alright, so checking the left-hand side, I want to take the top fraction, which is 10 sevenths. I want to divide it by 2. So you'll notice I put the top part of this fraction in parentheses. I end up with 0.714, whatever, some fraction. 0.71428571428, whatever. Okay, so there's that fraction. Now let's try 2.5 divided by 3.5. You can see we get the same decimal. Now, let me look to see what would have actually happened if I had dealt with this as 2.5 and 3.5. I would have had, let me just see, I would have had w over 2 equals 2.5 over 3.5. Cross multiply, I get 2 times 2.5 equals 3.5 times w. At this point, 2 times 2.5 is 5, equals 3.5 w, and w equals 5 divided by 3.5. So this is actually an argument for why it actually works out a little nicer if I work with fractions. 5 divided by 3.5, 5 divided by 3.5 comes out as some decimal, and I don't have the exact version of this number here based on the work that I did. Now, some calculators are able to try to convert this to a fraction from this point, and that might work for you, but you know, you're kind of relying on the calculator to do some of the work for you, and thus it doesn't always come out as expected. here I actually didn't have to rely on the calculator at all, so in any case, that number right there should be 10/7, the 5 divided by 3.5. And there are ways to get there, keeping it in this fractional form. For instance, if I notice that multiplying both the top and the bottom by 2 would give me integers on both the top and the bottom. That way, that's one way I could have gotten 10/7 there. All right, so one final little trick. If you've stuck with me to this point in the video, you get a nice little trick. Let's see. So if we have something that looks like this, 28 over 40 equals x over 100, typically I would do the product of those divided by the product of those. But you may have noticed a certain thing continually happening. We're always taking a product of two of the numbers divided by another of the numbers. And in general, well, I guess in this particular case, we would say this x is already on the top part of the fraction, so all I would have to do is multiply both sides of this equation by 100. And we end up getting 100 times 28 over 40. You can see that's what I wrote right there. This allows us to kind of solve this in one step as opposed to taking 2 steps. And in general, when we're solving these fractions, if you do kind of if this is the one you're trying to solve for, you would do the product of those and divided by the other one, the one that's diagonal from the number you're looking for. I'm not big on tricks like that. I don't generally show them first because they're not as useful as the general concepts that I tend to focus on in these videos. So that's why I waited until now to talk about it.